started. Okay. Ready? All right, this question says, which statement about the graphs of the inverse is true? They're symmetric about the y equals x. They're symmetric about the origin. They're symmetric about the x-axis, the y-axis. Well, here's the thing. Functions and their inverses are always symmetric about the line y equals x. And here's why. A function and its inverses, or a function and its inverse, is simply the exchange of the x and the f of x. So if I have a function that's defined to be this, the set of points for the inverse would simply be these values switched. And so it would look like this. It switches the domain and the range. One other way we can prove that or think about that, if you've seen this, is that any time that I have a composition of a function and its inverse, that always equals x. And so if you ever had to verify, they give you an f of x and a g of x, and they said something to you like, are the two functions inverses of each other? You just simply would take f of g of x if they, when you simplify, equal x. They're inverses of each other. So this is going to be a. They are symmetric about y equals x. Now, linear equations. This is an Algebra 1 type problem. However, we in Algebra 2, you're going to see several of these on here. What I would suggest that you do, these are both written in standard form. I would like to see it as ax plus by equals c, or simply take the constant term of each of these and put it to the other side. That's how we are used to seeing it. So in this case, we have 3x minus y equals a negative 5, and 2x plus 3y equals 4. I subtracted 5 from both sides, add 4 to both sides. Now to solve this, it's pretty simple. I love the linear combination method. The linear combination method is simply, I want to try to add the two equations together and see if one of the letters go away. They wouldn't. This would, if I just add them right now, I'd get 5x and 2y. That one of the letters won't go away. So I really wish this was a negative 3y. Because if I add them together, a negative 3y and 3y would be 0y, correct? So what I'm going to do is I'm going to multiply this entire row here by 3. And I get 9x minus 3y equals a negative 15. We're going to have 2x plus 3y equals 4. Now we use linear combination method. The y's go away, and I get 11x equals a negative 11. Divide both sides by 11. X equals a negative 1. So we automatically know that can't be this, can't be that. The way we find the y? Yes?
Why do you have a negative 5 in the top equation?
Very good. I wrote them in ax plus by equals c. I simply subtracted 5 from both sides, so I could get a number over here. It's easier for me when I solve for x.
Oh.
And I did the same thing here. I added 4 to both sides. Maybe I should have written that out for you. My bad. But sometimes I'll say it or do it mentally, which is bad, especially on video. So thank you. When I have x equals a negative number, what we're going to do now is we're going to plug it into one of the original equations and find y. So I'm going to pick this right here. And I have 3x's minus y. Go ahead and put plus 5 equals 0. I get a negative 3 minus y plus 5 equals 0. Negative 3 and 5 is 2. So it's a negative y plus 2 equals 0. Subtract 2, or you could just add y. And I get negative y equals a negative 2 divided by negative 1. Extra step, do it this way. Y equals 2. So this is going to be B. Don't be afraid to go ahead and write it all out. So you have plenty of scrap paper, you have pencil. We got a little chicken scratch up here, I'm sorry. but it's kind of the nature of the game sometimes. Let's suppose that you didn't know. You forgot how to solve linear equations altogether. Well, that's legitimate. Someone could say, "Hi, Mr. Schulze, I was looking at the test and they had these two problems I didn't know." Well, here's the kicker. These are the solutions. One of these is right, correct? If I plugged an x and a y into our original two equations, if it's true for both, it's the solution no matter what. All right? So I know, because I did all this work, that this is the solution. Let's look at this. 3x minus y plus 5 equals 0, and 2x plus 3y minus 4 equals 0. If I plug a -1 in for x and a 2 in for y, a -1 in for x and a 2 for y. Well, 3 times a -1 is a -3. -3 minus 2 is a -5. -5 plus 5, is that 0? Yeah, -5 plus 5 is 0. So that's true. Here we have a -2 plus 6 minus 4. Does that equal 0? Well, there's a -6 plus 6. That's 0 equals 0. It's true for both, so it's our solution. What would happen if it wasn't true for both? We'd have something like 4 equals 0. That's not really true. So if you don't know how to solve them, plug them in and see if it works. Plug them in and see if it works. Also a good strategy on the ACT, especially if you see a function that you've never seen. Plug in the values that they give you and see if it works. See if it works. All right, here's one. Here we have a system of 3 equations, 3 unknowns. We can solve this. We can do it by substitution. A little harder to do linear combination in this sense, but watch, it can only be A, B, C, or D, right? Now look. And this is going to be a little visually intensive, so if you'll follow me. X plus 5 equals y, or equals, x plus y equals 5. 2 plus 3 equals 5, right? Mm-hmm. Well, x plus z equals 7. Well, 2 plus 9 does not equal 7. That's not the one. 2 plus 7, there's x, remember that's x, y, z, right? X, y, z. 2 plus 7 is 9. That is not 5, so it's not going to be B either. A -2 plus 8, 6. It's not this one. Are you with me? So much easier just to plug it in, even if you do it mentally. -2 plus 7 is 5. A -2 plus 9 is 7. And 7 plus 9, y plus z is 16. That works. Has to be D. A lot of times people get up to the EOI and they forget there are other ways to get the answer. A lot of students, because of familiarity, they just see it. Somebody see this, and they think, I don't know. Pull back and say, hey, they give me answers. Plug them in, see if it works. If it works for all 3, it's a solution. Roots. I want to illustrate several things now. There are, in dealing with polynomials, or in this case, this could be a quadratic, it could be quartic. It's an even function, right? End behaviors are the same. You follow? So a root is the same value that would, for instance, if I had x squared equals 4. We took the square root of both sides. We have x equals plus or minus the square root of 4, which is plus or minus 2. So if I had a function, f of x equals x squared minus 4, we could say that we have 2 roots, right? Set it equal to 0 solved would be the same possibility. A root, a 0, and a solution are simply x equals some value a that would make it a point where the graph would touch across the x-axis. So watch this. A root, how many times does this graph touch the x-axis? 0. So it has no real roots. No solution, no real solution. This would have one solution. This would have two solutions. You follow? This would have no real roots. This would have one real root. This would have two real roots. It's almost a tongue twister. If you had a graph that did this, you would have 1, 2, 3, 4, 5 solutions. And so you would have 5 roots. Yes, it's a root, it's a solution. And let me insert a slide because I want to show you something. Watch this. This is critical to Algebra 2. 1, 2, 0. Here we have 3 solutions. We have 3 zeros. We have 3 roots. Now watch this. X equals a negative 2 is a 0. X equals 0, 0, and x equals 3 is a 0. There's a polynomial function. In fact, there's several polynomial functions, an infinite number of polynomial functions that would go through this. But I can rewrite this. Here I have solutions x equals a negative 2, 0, and 3. If I want to come up with a function, f of x, that would have these roots and these solutions, watch this, this is so simple. So very simple. Put 3 parentheses, put x minus in all of them. You follow? Then simply put these values in them. X minus minus 2, x minus 0, and x minus 3. Well, minus minus I add, I have x plus 2. Well, x minus 0 is just x. And x minus 3 is that. And we could go ahead and multiply them all together. But this corresponds to our solutions, our roots, and our zeros.
Would it ever be x plus 2, x plus 2?
Yeah. When I subtract x minus a minus, I get a positive, x plus 2. Does that make sense? So if we'll just do this, if they ever ask us write a function of least degree, which means have the smallest number of x's multiplied, okay? So it's x minus my solutions, however many solutions I have. And that's it. It's pretty easy. It's really, really easy to do. All right. Completing the square. Solving by completing the square is a technique they teach in Algebra 2, which is pretty simple. But if it didn't make sense to you when you first learned it, sometimes it's like your brain wants to shut down. It's not hard. If this was a perfect square, for instance, if I had a minus b times a minus b, that would be a squared minus 2ab plus b squared. We call this a perfect square because that is the same thing as a minus b squared, right? And so here's what we're going to do. They give us this equation, x squared minus 8x plus I don't know equals a negative 3 plus something else I don't know. Here's how we complete the square. It's very, very simple. Almost so simple that you'll miss it. To complete the square, to make this a perfect square, we take half of that value. What's half of the negative 8? Negative 4. And so we take a negative 8 over 2, and we square it. So we have a negative 4 squared, which equals what? 16. Negative 4 times a negative 4 is 16. That's common sense. 16. So we're going to add 16 here and 16 there. And all they say, they really don't want us to solve it. They just ask us a question. What number must that be to solve by completing the square root? What has to be 16? That's it.
We don't erase it.
I will not. Also, if this was a plus b, the only thing would change would be the middle term.
How come you don't do this? How come you don't do -3? Why do you do negative?
Because my x's are over here, and I want to complete the square. I want it to look like ax squared plus bx plus c. This is a general form of a quadratic. Here I have 1x squared minus 8x. And to make this a perfect square, I have to take half of that and square it. That way, and I'm going to go ahead and show you what you would get if you solved it because it's real important. Here I have 8x, or x squared minus 8x plus 16 equals -3 plus 16, right? We add it to one side, I have to add it to the other. Well, this now is a perfect square, right? That's what we try to do. And this would be in the form of x minus 4, the quantity squared. You follow? Remember this? Because I have twice a times b, and so here we have this, equals 13. If I took the square root of both sides, I would get x minus 4 equals plus or minus the square root of 13, which is irrational, leave it alone. Add 4 to both sides. X equals 4 plus or minus the square root of 13, whatever that is. It's ugly.
I like the first one.
Huh?
So I like the first one.
Yeah, the first way, well, it's just really easy. This is not a solution. This is a solution, but the solution to this question is only 16. The average person, the only reason you solve by completing the square is because you couldn't factor it. And for most of my students, if they can't factor it, they use and it's quadratic, they use the quadratic formula. All the formulas that you need are needed are given on the test. I think they even give you the quadratic formula. There it is. Ugly. It's okay, don't worry. This is nice. They give you the standard form of quadratic. They give you a quadratic formula. What they're asking you is to go ahead and use it. Here is the quadratic. The quadratic is x squared plus 5x minus 3 equals 0. Go ahead and put a 1 there. That's a coefficient there. So I have 1x squared plus 5x minus 3. So my a is equal to 1, my b is equal to 5, and c is equal to a -3. You follow? Now here's an easy thing to use quadratic formula. Everybody likes easy. This is my quadratic formula. First of all, write x equals. And then I want you to write all the symbols except where you see a letter. You're going to leave, don't leave blank, write parentheses everywhere, every place you see a letter. So all the symbols are going to be like this: a -b plus or minus the square root of b squared minus 4ac, all divided by 2a. Notice everywhere I saw a letter, I just left parentheses there. By the way, this solves every quadratic all the time. The quadratic formula always solves the quadratics. Now, let's look at A. Our formula has an A here and an A here. A is 1. So we're going to put a 1 right there and a 1 right there in the place of A. B is what? 5, right? Corresponds. So we have B is 5, and put 5 there, and a 5 there. And lastly, C is a -3. All right. Now we're going to simplify, which is a lot of people get frustrated with it. No big deal. We'll get rid of the parentheses and combine like terms best we can. So we have a -5, which is a -5. And here we have 25. 5 squared is 25. Minus 4 times 1 is 4 times 3 is times a negative 3 would be a negative 12. So minus a minus 12. And when I minus a minus, I do what? Yeah, or add. Yeah. Add. Divided by 2 times 1, which is 2. And 25 plus 12 is how much? 37. Remember, we have two solutions. We have a negative 5 plus the root of 37 over 2. We have a negative 5 minus the root of 37 over 2. So let's look up here. Let's look at our problems. The only ones that are possible, since we did this right, is going to be the ones that have the root of 37, right? And that's not good, that's not good. And here's the one that has the negative 5. They're actually making sure that we put the negative in it when we evaluate this. So it's got to be E. This can't be this one. Easy enough? Call that like plug and chug. We just plug it in and simplify it best we can. All right. Which direction does this parabola open? Does it open up or down? Leading coefficient's negative. Remember our original parent function, that opened up, right? The bowl. So if I put a negative in front of it, it would open what? Down. That's easy. So we're just it's not going to, which direction opens down? That's all they're asking there. Back to function notation and parent function knowledge. One of the easiest questions on the EOI or the ACT would be something like this. What's the y-intercept of the graph? An intercept is where it connects, right? Like an intersection that it intercepts the graph. What? Negative 3, exactly right. If x was 0, everywhere on the y-axis, x is 0, everywhere on the y-axis. And if I put a 0 in for x, that term goes away, that term goes away, and I get negative 3 out. So that's going to be my y-intercept of that graph, whatever that graph looks like. No matter your polynomial, the constant term is your y-intercept. If you don't have a constant term, then 0. All right. Which function represents this graph? Does it open up or down? Down. So since it opens down, it won't be one with a positive, right? Now the y-intercept is a negative 2 in all of these. Actually, this is a positive, so it can't be that one either. It's a negative 2 in both of those, right? So the y-intercept doesn't really help us a whole lot. What helps us is, does it look narrower? Does it look like it's stretched out, or does it look like it's compressed, a little chubbier? Using that word, but you know. It opens a little less narrow. It's wider, if you will. And so anytime this number is a fraction, it's less than 1, it's going to be wider than our parent function. Anytime that number, the absolute value of it, is greater than 1, it will be narrower. And so it has to be a. And when in doubt, guess what? You could graph them both on the TI-84. And if you graph these on the TI-84, this one would be that one, and the other one would look something like this. It would be much, much more narrow. Right? So you can plug them in. If you're going to graph it, remember, use parentheses when you have division symbols. It helps so much. So, all right. Fantastic. We're making good time. Oop. Again, which function is represented by the graph? This is a little bit easier function to analyze using our graphical analysis. Opens down, right? So the leading number is negative, correct? So it's got to be. It can't be this one. Can't be this one. What's the y-intercept? Yeah, it's 3, which is absolutely right. B. Fantastic. The y-intercept is 3. That's the one I can't do. That's B, and we're done. And let's go on.
Yeah.
What's that?
So I need to take the ACT.
I tell you what, the Algebra 2 and the ACT help so much.
I'm going to get 36. That's what.
Oh my goodness.
That's All right. A lot of times people get frustrated, but what I want you to look at here is this. What kind of function? This is a parabola. Opens down, right? Everybody know what form this is in? I mentioned it once earlier. This is vertex form, right?
Yeah.
If we would have had our original parabola look like this, but this one is shifted to the right 16 units. Way over here, 16 units and up 4. All right, it opens down. Now, that's not a perfect graph. It's just a sketch, mental sketch that I can know what we're dealing with. They're asking, if this is a function that determines profit, blah, 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 what's the maximum profit? Where is that going to be? Well, that's going to be right here, correct? And what point is that? It says a company is selling an item that determines the profit from selling the item for a price of X dollars given by the function below. Which price will maximize the profit? Well, what's the highest value we have in there? Now, I say what's price. X is the price, right? So I'm going to have the maximum profit. My maximum profit is $4. My price is 16, right? Because when I input $16, I get a profit of 4. Does that make sense? So this has to be C. So what would make this the highest point on the graph? Is that confusing? A little, maybe? Not so much? Yeah, what X value, what price in X dollars would give us the maximum profit? Well, the maximum profit, my output is going to be profit, right? So if I put 16 in here, I get 16 minus 16, which is 0. 0 squared is 0. Times that, I get $4 profit. Right? That's my maximum profit. But the question says, which price, which X? It's one of the things you might do when you see something like this. Which price? Come up here and underline. They told me the price is the X's. All right. The profit would be the function or the Y value. So let's see. The only way, and I'm trying to think if I can write all these up here. You have hyperbola. You also can have at the end of Algebra 2 some different types of parabolas. You have parabolic functions. You have ellipses and circles. I'm going to throw before I do this one, let me see. Oops, I messed up here. Sorry. There's the answer. I didn't mean to do that. Let me put a new slide in. X squared, I'm sorry, X squared plus Y squared equals R squared. That's the equation of a circle. It's the equation of a circle at the origin. The center is at 0, 0 of this particular circle, where R is the radius. Now, if I want to move that circle anywhere, for instance, if I want to move this 2 units to the left, and because I have Y squared and this is R squared there, I'm going to have to do opposite to what I would think here. I'm going to use it, move it 2 units up. And my radius is 2, so that's going to be 4. My center is going to be at 2, 2. Does that make sense? My center will be at 2, 2, just the opposite of these values. Ellipses are a little bit different. They're usually like A over, let's see what it is, X squared over A squared plus y squared over b squared equals 1. Ellipses always look at this like this one. Now ellipses can be centered on the x or y axis, or they can be moved. And I subtracted some things in here. All right, it gets kind of ugly, but it can be. I could have, for instance, an ellipse like this, or an ellipse that's like that, or maybe one that's over here. Yeah, it's a squish circle. But the general form of ellipse is simply the x squared. Oh, I need to go back. We can actually see the problem that we had. Here we go. Here we have y squared over, let me erase all that. Our x squared over 50 plus y squared over 25 equals 1. This may not be a perfect square in your mind, but we could take the square root of it if we needed to find the co-vertex of the right. Or I'm not sorry, the ellipse. This is the ellipse form. The hyperbola would have a negative in here. All right. If they ask me about hyperbola, there would be a negative in there. So it is an ellipse, and that corresponds. Easy question here now. What is the equation? Here's where you have to be careful. What is the equation of a circle with center here and diameter? Now, diameter is twice the radius, right? So if the diameter equals 2r, the diameter is 6, then my radius must be 3, right? So pretty simple. Now all I need to do is put it in the equation for a circle. X minus 4 squared plus y minus 2 squared equals 3 squared. Remember that's x minus something squared, y minus something squared equals r squared. And so the center of this circle is indeed a negative 4 comma 2, but really all we needed was what? 3 squared, which is what? 9. So we look at this, x plus 4 squared plus y minus 2 squared equals 9. That only corresponds to one of them, which is D, right? Yeah. All the other ones are just simple mistakes. People would just subtract, or maybe they subtracted one, but not the other. This is an easy problem. We don't even have to think about it because it's already in vertex form. Vertex form. I have a parabola like this. This is vertex form is always y equals x minus h squared plus k, where h comma k is the vertex. In that case, all we have to do is know that that's 1 comma negative 9 for the vertex. My x value of the vertex is a negative 1. And the y value is, I'm sorry, it's 1, and the y value is a negative 9. Boom. Don't make it any harder than that. Let's say you were having trouble. And you said, Mr. Schulze, I forgot. But I have a graphing calculator, and I know that I can do things on the graphing calculator that make my world seem simpler. Now, this is a lot more steps than what I would take. But if you had trouble, you could always go over here and put parentheses, x minus 1, close parentheses, squared, minus 9. We're going to graph this. All right? Now, all we need is a vertex, right? That's what they ask. But I don't know it, so I want to make the calculator do it for me. Now, is this the bottom of the graph, or is this a minimum or maximum? It'd be the minimum of the graph, right? Because it goes up after that. If it was a hill, it'd be the maximum. So, second, calculate. Look here, minimum. It's so simple. Now we're going to go down here. We have to. The calculator is asking, what do you want me to look at? what area of the graph you want to look at. So we're going to give it a left side and a right side, and then just hit enter twice. So we're left of the bottom here, and we're going to go to the right of the bottom there, and it's going to look between that x value and that x value, and it says guess. Now look here, here's what I want you to be careful of, because a lot of people get upset. The y equals a -9. That's right, but look at this. The graphing calculator approximates sometimes. It gets infinitesimally close, but it's frustrating. So it sees a 0.999999987 is really close to what value? It's 1. So as long as you understand that, it's okay. Now, if I got closer, if I force those x's a little closer, it could be a lot more accurate. So you can always do that. While I'm here, how many solutions does this thing have? What? It has 2 solutions, and it has 2 zeros, and it has 2 roots. Yep. It's nice. I don't know. Here, let me clear this out. All right. Logarithms. Let me get a blank screen. What's that? Y'all love logarithms? I love logarithms. They're my favorite. I'm going to show you something about logarithms. And logarithms are the inverse of exponential functions. I'm going to show you in 10 minutes logarithms. All right? But I have to start with one that looks normal to us. First of all, if I had a function y equals 2 raised to the x, this is called an exponential function, right? For every the exponent position, we have an x. That's my variable. So if I made a table of values, I would have, let's see, if I had put a 3 in for x, 2 to the third is how much? 2 times 2 times 2, which is 8. Then if I inputted a 2, 2 squared would be 4. If I put a 1, I get a 2 out. Well, if I input a 0, 2 to the 0, that gives me a 1 out. Well, okay, so what? Mr. Schulze, that's crazy. You know, 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. It works. Well, a -1, if I put a -1 in there for x, that gives me 1 over 2, or a half. -2 would be 1 over 2 squared, or a fourth, and on it goes. Let's look at the graph, really easy. And I'm setting this up for logarithms, you'll see. At 0, we're at 1, at 1, we're at 2, at -1, we're at half. This thing looks like this. This gets arbitrarily close to 0, never actually gets to 0. So I have a vertical asymptote. This increases without boundary, keeps increasing forever and ever and ever. The domain is all real numbers. It can go infinitely to the left and infinitely to the right. The range is 0, parentheses 0, to infinity. We can never actually get to 0 on the range. You with me? Kind of follow? Now I want to look at logarithms. Well, logarithms are the inverses of exponential functions. Let's do this. Log base 2 of x, if I had a function like this. Now, I've already told you they're inverses, so we can switch the x's and the y's because it changes our inputs to our outputs and our outputs to our inputs, right? Right. Sorry. So if this point right here is 0, 1, and this point is 1, 2, and over here we have a -1, 1/2. If I would switch the inputs and get 1, 0, I'm at right here, right? Then I have 2, 1, which would be right about here. If I have a half, -1, so here a half, -1 would be right here. This is the logarithm of x. Now, if I put those on the same graph, guess what? They are symmetric about the line y equals x. So they are inverses of each other. It makes it really, really, really simple. Dum, dum, dum. Now, we can shift these functions just like we shift everything else. And let's do this. Go back to the question and then we'll hit another. Was that the one? Or is there another one? All right. Inverse function. Here, the calculator understands two logarithms. It understands the natural logarithm and base 10. Anytime I don't have a base right here, that's understood to be base 10. So this is actually log base 10 of x. Okay? The inverse would be an exponential function that would have 10 as its base, which would be this. And that's it. Let's see. This is almost too small. Even on your, I think it says log base 7. This is 3 log, no, it's base 3. 7 equals x. Now watch this. What?
I thought you can't read it.
It's really small. I'm sorry. It's awful. But watch this. This will make it really simple. If there's a fraction there, then it'll be the wrong answer. But I'm seeing this, and I copied this right from the state website, so it actually will be clear if you took the test. If it is wrong, I'll tell you which one it is because that'll tell me what the answer actually was. These two functions are inverses of each other. Okay? Let me show you something. If I had if I wanted to take the inverse of that, then I could exponentiate that. So this, in a sense, undoes that. You follow? I get x, or 7 equals x. Now, if there's a fraction in here, or if there was some other thing in here, then it's going to be one of these other answers. But it's a. I'll show you how to use those in a minute. It is a. I'm so grateful that it is, because I couldn't see it for anything. Let's insert a slide. Watch this. I'm going to show you how to use logarithms as a tool, a mathematical tool to just manipulate the equation. All right, real simple. Let's take 2 to the x equals 8. In your mind, you already know x has to be what? 3, because it has to be 2 times 2 times 2, right? But if I wanted to solve this using an algorithm, using mathematical notation, I can't divide by 2, that help. Because this isn't 2 times x, this is 2 raised to the x. So what I have to do is I have to undo both sides. I have to undo this. And the way I undo it is this. The log base 2 of 2 dx equals the log base 2 of 8. This undoes that, and I get x equals the log base 2 of 8. Now this is an answer. Sometimes on the EOI or the ACT, that will be your answer. And you have to know how. I thought it equals 3. Well, we can make the calculator give us the right answer. Aren't you glad? The calculator only understands 2 base, so we have to use the change of base formula. Change the base formula on the calculator looks like this: log 8 divided by log 2. This will always give us the answer. Now, log 8, close parentheses, divided by log 2 is 3. Yay, we knew it was 3. All that worked for 3. But what if they had something that you didn't know? What if you had 2 dx equals 21? Well, I know 2 to the 4th is 16, 2 to the 5th is 32. It's got to be a number between 4 and 5. But if I want an accurate number, what I have to do is take the log base 2 of both sides. Again, a lot of times students don't write this step. I do because I want to remember it. Log base 2 of 2 to the x equals the log base 2 of 21. This undoes that. X equals the log base 2 of 21. And the calculator gives me the decimal, which is the log of the big number of 21 divided by the log of the base. And you simply would put in there log of 21 divided by the log of 2, which is 4.3923. Makes sense because I knew it had to be between 4 and 5. That's your answer. Move on. Make sense? All right. Lastly, and probably most confusing part of logarithms is expanding and condensing logarithms. There's 3 rules: expanding and condensing. I'll write them down really quick. First one, I have the power property of logarithms, which is log base a of u to the n equals n log base a of u. Blah blah blah. All these letters. That's easy. If I want to write this, if I had the log base 2 of x to the 3rd, I simply can rewrite that as 3 log base 2 of x's. That's the power property of logarithms. This is a whole lot easier to deal with than this. We have a product property. Product just simply means we have 2 things: the log base a of u v. That's the same thing as the log base a of u plus the log base a of v. This is always the case. And the reason that comes in helpful is if I had the log base 5 of 2x and I want to get x by itself, there's a product there, right? So that's the log base 5 of 2 plus the log base 5 of x. This is from going from this product, logarithmic product, to this is called an expansion. If I gave me this, I could go backwards. The 3rd rule, and then we're going to mix it up and I'll go on, is the quotient rule, or quotient property. Log base a of u over v is simply log base a of u minus the log base a of v. Now, up to the advent of the calculator, the logarithms was the latest, best advancement in mathematics. And to think that we initially went to the moon, or the space program started out with people using logarithms, and the tool that they used to interpret logarithms was really fun, not really fun, but innovative way of using them was using the slide rule, which had a list of logarithms on it. And they could do a lot of complicated math using logarithms. It was really, really easy for them if they had that. It's easy for you to use a calculator. But they had all these rules, and they knew that if they just could manipulate those rules, they could get numbers out. In fact, when the calculators first came out, some of the guys, slide rules were much, much faster than that. Let's look at this. Log base a of x over, let's say log base 7 of x over 9. I want to get the x by itself, use quotient property, expand it. That gives me the log base 7 of x minus the log base 7 of 9. See, I could, if I had a logarithmic equation, I could get the x by itself, move the other stuff to the other side, and then exponentiate to base 7. Boom, boom. Now we're going to mix it up in a problem, and then I'll go on with our slides. We may run into a few more if we have time. I want to spend the last 20 minutes on simplifying irrational denominators, because that's a pretty large portion of the EOI as well. Let's expand this. Log base 3 of 3y squared over x. We're going to expand this. We're just going to make it as big as we can using the rules of logarithms. All right? Now watch this. We're going to deal with one thing at a time. So that's usually the best way to do it. Let's do the quotient property first. Get rid of the denominator. Here we have application of the quotient property is the log base 3 of 3y squared minus the log base 3 of x. There's the quotient property. You good? Now we're going to use the product property. Well, that's right here. That's the log base 3 of 3 plus the log base 3 of y squared minus the log base 3 of x. Almost finished. You do this a little bit, you can do it really quick. The power property, we just bring the 2 in front of this, we're done. That's it. That's expanded. 1 or 2 problems on the EOI like that. But they're really easy if you know how to use those 3 rules. If we had to condense them, that tells me in product, this times this is a power, so I can move that over there. 3y squared, that's in the denominator quotient. 3y squared over x. Talk yourself through it. How do you feel about that? Overwhelmed? Anybody got a headache? Sometimes. Sometimes that's the case. Which of these represent the solution? 6 to the x equals 21. So we've kind of set this up already. Again, they don't ask us for a specific number, but 6 to the x equals 21. If I want to solve it, I have to take the log of what base? Base 6, right? So I've got to take log base 6 of 6 to the x equals the log base 6 of 21. This undoes that, so I get x equals the log base 6 of 21. None of those look like that, but my calculator, this is the change of base formula. It's the same thing as the log of 21, the log of the large number divided by the log of the base. So that's going to be the log of 21 over log 6. This means the log base 10. As long as you know that, anytime you don't see the base there, it means base 10. The calculator also understands natural log. So if I had natural log of 21 over the natural log of 6, that would also equal the same number, but they don't give you that. I don't want to confuse you. Okay. All right. So many times people get frustrated. I'm going to show you I'll show you the algorithm, but the calculator is the way to go on this. All right, the calculator is the way to go. What exponent corresponds to radical? Radical x equals what? X to the 1/2. Anytime I have a logarithm, log base 10 of 10 root of 10, which is 10 to 1/2. I have a question here. What exponent must this base have to be this number? Well, that's that exponent. Okay? If you didn't know any of that, of course it is b. If you didn't know that, go your handy dandy calculator. Log square root 10. 0.5. That's half. So when in doubt, just plug it out. Plug it in. I don't know. All right. This is a little ugly, but it's okay. Now plug this in the calculator. I should get a value. This is log base 3 though, so I'm in 4. We shall write this out. Log base 3 of 1 over 27. 27. Can I rewrite this as an exponent of 3, this fraction right here. What is 1/27th? That's with 3 as a base. What would that, how can I get there? Well, 3 times 3 is 27, right? So 1/27 would be 3 to the negative third. You with me? Remember, the 3 to the 3 is 27. Then 3 to the negative third would be 1/3 cubed, which would be 1/27, right? Now here's the question. What exponent must 3 have to be 3 to the negative 3? Well, it's a negative 3, right? And where's the x at? Do they have x? This is right off the state website. Oh, bum, bum, bum. Because there's no way that's going to equal 27. That's an aberration. That's not going to be that's a wrong answer. I'm hoping the state is updating that problem. That's from their questions. I know, I apologize. I get all the way into the problem, and I should have looked for the x. I don't see an x there.
Can we just change the problem?
Yeah. Hey, doing it. Okay.
27.
27. Now, let's disregard this for a while. Let's at 27x. All right. This, remember this one does that, and so that simply is 4 times a negative 3. Negative 12 equals 27x. Divide both sides by 27. X equals a negative factor of 3, and 3 out of there, I get negative 4/9. Sorry. Can't solve for x if it's not there.
What's this? What's the answer?
I will reveal it, but it's not. Yeah, D12. They had 12 up there, so.
You have 12 right there.
Yeah, there was a 12 in there. I don't. This was one of their practice problems. In fact, I've seen this several
Well, Tom,
types of problems.
Am I incorrect in saying that sometimes questions that are even on the test get thrown out?
Yes. Yeah, sometimes they have a bad question, especially some of the released items.
And that could have been
one of them. Yeah, it's like, wait a minute, that is not. And they would only know it if someone either appealed the test or someone was going through checking the answers, which they should do. And they probably do have those countermeasures in there. All right. Here's a problem that a lot of people get frustrated with, but don't. We just already talked about this. They're going to throw these at you in different random orders, and this is why I've got it set up this way. What is a root? Which of these is a root of this? Okay.
12.
Well, I don't know. I don't think so, but watch this. This is a cubic function, right? Probably something that might go up here, and a root and a 0 and a solution are all the same, right? They're the same number. So please, let me show you how to use the calculator to do this. It's so simple. We're going to punch in the exact formula here. 3, or x cubed. There's the exponent key right there. Cubed. Minus 3x squared minus 4x plus 12. Now my graph window is on a 10 by 10 window. I'm not going to see all of this, but watch this. I've got 1, 2, 3 zeros here, right? And if I hit second calculate, look at number 1, value. What they're asking there is that you put an x in here. I've got 4 x's, right?
Mm-hmm.
If I plug in a negative 3, hit enter, it's a negative 30. That's not a 0. A 0 is going to be here, here, or here. So I put in a 3. That's a 0. Do not do any more work than you have to. That's a 0. I'm done. Does that make sense to you? No, does not make sense.
I don't have one of those calculators set over the no.
Do
Oh,
I
let me
use
show
my-
you. Your calculator will do this, but it won't do the graph. Here's what your calculator needs to do. Anytime you have the regular scientific calculator, but you do also have option for, on the EOI, you can do this. Because you have parentheses.
So that calculator will be on the screen, right?
Yes, that calculator, there's an electronic version of the calculator on the Algebra 2.
Is it that one or is it just a regular?
It's that one.
That one?
It has the same keys and everything. This is the standard for the most part. I've never seen anything else but the 84 or the 83. It may be 83 or 84, but they look exactly the same. On your calculator, there's a standard scientific. If you did this, if you punched in a -3, you're going to get a 30 or whatever it was. If you punch in a +3 here, it's going to equal 0. If it equals 0, it's a root, it's a solution, it's a 0. I hope I've said that enough because you will see that again. And so all you have to do is punch it in using parentheses. Should be great. All right. Now, look at this. First of all, based on roots, zeros, and solutions. Now, this is written in factors, right? If I set those factors equal to 0, I'd get solutions. The opposite of these values would be x-intercepts. You with me? So, I have an x-intercept, what's here at -5, -2, 1, and 4, right? So if I wrote this out as x minus, x minus, x minus, x minus, put in a -5, -2, 1, and a 4, minus minus is positive. This first number I don't really care. I do care that it opens up. End behaviors are the same, so it has to open up, right?
Supposed to be positive.
Yeah, it can't be one of these because if it's a negative even function, they both open down or go down. You with me? So
Wait, is that a -5 or a +5?
there was a -5, which is a +5. I changed it. When you minus a minus, you add. So I went ahead and changed it to make sure that when I subtract the negative, it's the same as adding. So it has to be this one. No other thoughts really needed. And if you needed to do this, you could punch this exactly into the graphing calculator, hit enter, and it would appear to be this one.
Oh, so I could just graph the answers.
Yes. If you have the graph and they have you have them all, you can just graph it and see which one matches.
Okay.
Make sense?
Yeah.
Awesome.
Did you go?
I'm going to simplify just a minute. All right. Another graphical analysis takes up a lot of the EOI. Graphical analysis, just tell me something about the graph. Here's a graph. It says, what's the x and y intercepts of this graph? Well, we have one at -1, 2, and 7, right? So x-intercepts always are coordinates like, a negative, or an x comma y, right? So it's -1, 0, 2, 0, what did I say, 7, 0?
Yeah.
Those are the x-intercepts. And the y-intercept is a positive, yeah, I don't think it's,
28, but it doesn't look like it's on.
that's one I have to choose, wouldn't it? The
It looks like
y-intercept,
it's on 20.
it does look like it's on 20. It seems to me like 28 would be somewhere in here.
Yeah.
Based on what's the best answer?
A.
That's it. Sometimes they'll say what's the best answer, and you're just going to have to guesstimate and go on. It's horrible. My math nature just goes completely contrary to that. All right, what I want to do is I want to talk about simplifying complex fractions, simplifying or rationalizing denominators as well. So let's look at this. 1 over radical 2. When we have a fraction or a rational problem, we can't have radicals in the denominator. One of the things you can always do to a fraction is multiply by 1, and it doesn't change its value, right? Anything other than 1 would change its value. Don't want to do that. So, but we have to use special ones. And in order to get a radical 2 out of the denominator, to rationalize, we have to have a rational number in the denominator, make it a good fraction. We're going to multiply this by a special 1, but the special 1 is going to be radical 2 over radical 2. This divided by itself is just 1, right? So we have 1 over a radical 2 times a radical 2 would be a radical 4, which is simply 2. That's the shortcut. You with me? That's the shortcut. That works great. We do it all day long. 5 over radical 3. We'll multiply it by radical 3 over radical 3, which gives me 5 radical 3 over 3. Easy. Easy enough, right? Now I'm going to mess it up. 2 over 1 minus a radical 3. I got a problem here, obviously. I have a radical denominator, but we have a binomial situation. This is a complex number. We have a real portion and a rational portion, or a irrational portion. What we're going to do is we're going to multiply this by 1 here, but the special one's called the conjugate. Conjugates are very easy to find. If I have a minus radical b, the conjugate of that is a plus radical b, and vice versa. All right? So watch. The conjugate of this is that with a plus sign of it. I'll show you why we do this really quick. I'm going to FOIL this out. Or multiply. Let me just multiply it vertically first so you can see it. I have 1 minus a radical 3 times a 1 minus a radical 3. It's not hard though. Negative radical 3 times negative radical 3 is a positive radical 9, which is just 3, right? You follow? Negative radical 3 times 1 is just a negative radical 3. Oop. I apologize. One of these has to be positive. We start over? No. Sorry. I want to get a good illustration because this is where I'm going. I got to mess up a little bit, I guess. There we go. Negative times a positive is negative. Negative radical 3 times positive radical 3 is a radical 3. Or it's just 3. Radical 9 is just 3. You with me? Then we have a negative times 1, which is a negative radical 3. We move over like we would any two-digit number. I go 1 times a positive radical 3 is a positive radical 3. 1 times 1 is 1. Add them all up, we get 1. These go away. Negative 1 of those and positive 1 of those, and none of those. Minus 3, which is just negative 2. The reason we did this is because we needed to have some convention to get a radicals out of the denominator. All right, now for the shortcut. So if I could tell, you want a shortcut. Almost getting close on time. All right. This times this is this minus that times that, which is going to be that. Distribute 2 plus 2 radical 3s. Simplify the denominator. Everything in the numerator is divided by a negative 2, right? 2 over negative 2 is a negative 1, and that divided by a 2 radical 3 divided by negative 2 is a negative radical 3. That's what the answer looks like. Ugly, but it works. Yeah. There. What's that? Oh, I know. It's frustrating some, but it gets it. But it's not always identical. Some of them can look really, really frustrating. One other thing I want to talk about is imaginary numbers. imaginary numbers are, I wish we could use some other name for imaginary numbers, because they're like an imaginary, why don't you learn about them? But they're important. It's used in some cases to describe capacitive and inductive voltage or current in electronic communications. They have to use it. It's kind of funny. 2,000 imaginary units of voltage could kill you. They use it not as if it doesn't exist. They have to use it to identify something that is out of phase, or 90 degrees out of phase. The imaginary number plane. Remember, we have a real number plus a imaginary unit. Let's just do that. On the imaginary number plane, if we have 1 plus I, we have 1 unit in the real direction, 1 number. That's that point right there. 1 plus I units. And that's going to be an imaginary number. But these are really easy to graph. If we had a negative 3 minus 2I, that's a negative 3 real, and a negative 2I, which is this point right there. All right. Now, I'm getting all over here, but I've got to run out of time. I've got to do this. Let's talk about what I means. We knew that radical 4 equals 2, right? What times itself equals 4? That's what the radical means. That's 2 times itself equals 4. So, but up until Algebra 2, we did not know what a radical of a negative 4 was. And so we said, well, that's a whole lot like a radical negative 1 times a radical 4. We know that a radical 4 is 2. But what is a radical of a negative 1? Well, in Algebra 2, we defined that to be equal to I. That's an imaginary unit, which is simply I times 2 or 2I. And here's where it gets fun. Yeah, I'm a nerd. I have a pocket protector, and I'm qualified. Radical negative 1 times a radical negative 1. Using our rules of radicals would be just a negative 1, right? Well, that's the same thing as I times I, which is I squared, which is a negative 1. Good enough? I times I is a negative 1. I squared is a negative 1. Now watch. I'm going to do at least the power 4. It's kind of fun one. I to the third, well, that's the same thing as I squared times I, right? But I squared is equal to what? Negative 1, and that's just simply a negative I. I'm sorry. Information overload, just about. I get this sometimes. Now watch this last one for right now. I to the fourth is the same thing as I squared times I squared, which is the same thing as a negative 1 times a negative 1, which is 1. And then the pattern would start again if I went to the 5th, the 6th, the 7th. Are you lost? All right. Let me show you. Make it so simple. Yeah, YouTube at this point. It happens. Let's take this 2i times 4 plus 3i. We're going to simplify this. All right? We'll distribute. We're going to use our rules of multiplication, rules of algebra. It works the same. We're going to treat I like it's a variable. It's not. We're going to treat it like one though. 2i times 4 is 8i. 2i times 3i is 6i squared. But you have to know what a 6 or what an I squared is. What is an I squared equal to?
Negative 1?
Yes. See, you got more than you thought. 8i plus 6 times a negative 1, which would be 8i minus 6. You can rewrite it as a negative 6 plus 8i. Don't know why you would, but sometimes the answer may be given in this form rather than that. All right. 8i. Again, the key is I had to know what an I squared was. I didn't know if I was going to be here. I'm glad I'm at this place. You're a nerd, this is your stuff. All right, we're going to rationalize the denominator. All right. What does that mean? That means we want to get I out of the denominator. And the way we do that is we're going to use, similar to what we did with roots or radicals, we're going to use the conjugate of this. Anybody hazard a guess of what the conjugate would be? What was the conjugate when we had radicals? Well, multiplied by a special one. 3 plus 5i. You with me? Remember when the conjugate was something minus a radical? We had something plus. If it was something plus, we had something minus. The conjugate is always going to be the same thing, except the middle term will be the opposite sign. So, I'll go with it now. Now we're going to FOIL these out. Remember we had two binomials multiplied by each other and you FOIL them? I'm going to use the FOIL method on both the numerator and the denominator. I'm going to do the denominator first. First times first is 9. 3 times 3 is 9. Outer is 15i. Inner is a negative 15i. See that middle term is going to go away? And the last is going to be a negative 25i squared. We'll get there. I'm going to do the numerator first, which is 6. Outer is 10i. Inner is 3i. And the last is 5i squared. Now we're going to simplify. I slipped into redneck mode. I'm sorry. Now we're going to. Even teachers get tired from time to time. So we're going to combine like terms, and then we'll deal with the I squared at last. Okay? So in the numerator, these two are like terms. So we have 6 plus, that's 13i. You with me? Down here, those two cancel. Now, what does I squared equal? Be very careful.
1.
Negative 1.
Negative 1. Now watch. If this negative 25 or minus 25, if that was a negative 1,
It'd be positive.
and if this was a negative 1 here, that would be a negative 5, right? 6 minus 5 is how much? 6 minus 5 is 1. And 9 plus 25 is 34. And that can be written that way, or 1 over 34 plus 13i over 34.
I get it.
I know, it's weird. You're like, I don't know what I got, but I kind of got it. You'll have problems on there like that. The only other thing that I would suggest that you might want to study is, and I'm going to do it. I'll do a couple. I got a couple minutes left. I'm not trying to kill you with new concepts. It's just I don't have faith numbers. What's that? Yeah. Let's do this.
Not real.
A to the 5/3 power. Sometimes they want us to rewrite that. This is a rational exponent. Now watch this. It's real simple. We're just going to rewrite it using different notation. This is the exponent. This is the root. Anything in the denominator is the root. So watch this. This also equals the 3rd root of a to the 5th. And that also equals the 3rd root of a raised to the 5th. Okay, you just need to be able to do that. There's going to be some on there that'll say, hey, there's some rational exponents, deal with that. I had a to the 5/3 times a to the 1/2. Properties of exponents, that's a to the 5/3 plus 1/2. Common denominator, combine the numerators, and common denominator would be 6, right? But I have to multiply this by 2 over 2, and this by 3 over 3. That would be a to the 10 6 plus 3 6, or a to the 13 6. Yeah. Might be one on there, but you just need to know how to manipulate rational exponents. Is that good? Anything else that you think you might have trouble with? Feel like you're done? There's a lot of information. I appreciate you all coming today, and those that are viewing on the internet. If you have questions, you can email me at tom.schulze@epiccharterschools.org. Thank you so much.